Hey guys, welcome back. Tonight, we're going to explore something invisible, unstoppable, and quietly terrifying in the most soothing way possible. Dark energy. You've probably heard the term before. Maybe in a documentary you half-watched while folding laundry. Maybe in a headline you scrolled past at 2 a.m. when sleep refused to come. Maybe in a conversation at a dinner party where someone mentioned it confidently and everyone nodded along, pretending to understand, while secretly hoping no one would ask follow-up questions. And here's the thing, that's perfectly okay. Because even the scientists who discovered dark energy don't fully understand it. Not really. Not in the way they understand gravity or electromagnetism or the behavior of light. Dark energy remains the universe's biggest mystery wrapped inside its most important force. It makes up roughly 68% of everything that exists, more than stars, more than planets, more than all the galaxies combined. And yet, we can't see it. We can't touch it. We can't bottle it up and study it in a laboratory. We can't even detect it directly with our most sensitive instruments. We only know it's there because of what it's doing. It's pushing, gently, constantly, everywhere at once, and it's accelerating. The universe isn't just expanding, a fact we've known for nearly a century. It's expanding faster with every passing moment. Faster today than yesterday, faster this year than last year, faster this billion years than the billion years before. Galaxies that were once within theoretical reach are now drifting away. Stars that ancient astronomers might have one day visited, given enough time, enough technology, enough determination, are receding into the darkness. And eventually, in the far, far future, they'll be gone forever. Not destroyed, not exploded, not consumed by black holes or burned to cinders, just unreachable, moving away faster than light itself can travel, slipping beyond a boundary from which no signal, no spacecraft, no information of any kind can ever return. This is what dark energy does. Quietly, patiently, without malice or intention. It stretches the fabric of existence itself, and it doesn't care whether we understand it or not. By the end of this journey, you'll understand what dark energy is, or at least what we think it might be. You'll understand why it matters, not just to cosmologists and physicists, but to the story of everything. And you'll understand what it means for the future of the universe, from the largest galaxy clusters down to the smallest, quietest corner of your own life. You'll also understand why this force, this invisible pressure, is both the loneliest and most beautiful truth about the cosmos we inhabit. Before we go any further, if you find this kind of calm exploration valuable, a like or subscribe genuinely helps the channel grow. It's a small thing for you, a single click, but it makes a real difference for me. And if you enjoy the video, maybe leave a comment. Tell me what you think, but only if you actually want to. No pressure here, just gratitude. Now, let's begin. Dim the lights if you haven't already. Turn on a fan if that helps you drift. Adjust your blankets, shift your pillow to that perfect angle, and let your breathing slow. Let your shoulders drop. Let your jaw unclench. Tonight, we're going to drift outward together, past the walls of your room, past the glow of streetlights and the hum of your city, past the edge of the atmosphere, past the moon hanging silent in the void, past the sun burning alone in its corner of the galaxy, past everything familiar and everything you've ever known. We're going to keep drifting until we reach the spaces between galaxies, those vast empty gulfs where nothing seems to happen, where light takes millions of years to cross from one island of stars to the next, where silence isn't just the absence of sound, It's the absence of everything. And there, in that emptiness, we'll discover that something is happening after all. Something slow, something relentless, something that has been accelerating since before the Earth existed, and will continue accelerating long after every star has burned out. Have you ever wondered what it feels like to exist at the edge of the observable universe? Not as an astronaut with schedules and missions, not as a scientist with instruments and equations, but as a quiet observer, floating in the space between clusters of galaxies, surrounded by distances so vast they stop feeling like numbers and start feeling like philosophy. What does silence mean when there's nothing nearby for millions of light years in any direction? How would you know if you were drifting, or if everything else was drifting away from you? What would time feel like when change happens so slowly that centuries pass like heartbeats? What does it feel like to realize the universe is leaving you behind? And slowly, as you settle deeper into your pillow, as your thoughts begin to soften at the edges, you begin to sense something strange. The stars above you aren't just distant, they're retreating. Not quickly, not violently, not with any drama or urgency, just steadily, as if gravity itself decided to take the night off, and something else, something older, something quieter, something we don't have a complete name for, took its place. You are now floating in the age of dark energy, and everything, very gently, is moving apart. Now, we drift back in time, not to the beginning of the universe, but to the beginning of an idea. For most of the 20th century, cosmologists assumed one thing with near total certainty: the universe was expanding. Yes, Edwin Hubble had proven that in 1929. But gravity would eventually slow that expansion down. It had to. It was the only outcome that made sense. Think of it like this. Imagine throwing a ball straight up into the air. The moment it leaves your hand, it's moving upward, fighting against gravity. But gravity doesn't give up. It pulls constantly, relentlessly, and eventually the ball slows. It reaches a peak, it stops, and then it falls back down. The universe, scientists believed, was that ball. The Big Bang was the throw. All that matter flying outward, galaxies rushing away from each other, that was the upward motion. And gravity, the combined gravitational pull of every star and planet and black hole and atom in existence, was supposed to be the force that slowed it all down. The only question was, how would it end? Some scientists thought the universe had enough mass to eventually halt the expansion and reverse it. Everything would stop moving apart, hang suspended for a cosmic instant, and then collapse back inward. A big crunch, the opposite of the Big Bang. A universe that began in fire would end in fire, compressed into a single point of infinite density. Others thought there wasn't quite enough mass for a full reversal. The expansion would slow, yes, but never quite stop. The universe would drift toward a quiet equilibrium, forever expanding but at an ever-decreasing rate. A gentle fade into stillness. Stars would burn out, galaxies would dim, but the outward motion would continue, slower and slower, asymptotically approaching zero. Either way, the expectation was the same. The universe was decelerating. Gravity was winning, even if slowly. The cosmic expansion was losing momentum with every passing eon. This made intuitive sense. This matched every equation. This fit neatly into the framework of general relativity that Einstein had gifted to the world decades earlier. There was just one problem. It was wrong. Not slightly wrong. Not a minor adjustment. A decimal point out of place. Fundamentally, catastrophically, beautifully wrong. The universe wasn't slowing down. It hadn't been slowing down for billions of years. Somewhere along the way, something had changed. Something had taken over. Something was pushing outward, against gravity, against all expectations, accelerating the expansion faster and faster with every passing moment. And in the late 1990s, two teams of astronomers would discover this by accident, looking for one truth and stumbling into another entirely. But that story deserves its own moment. For now, just sit with this. For most of a century, humanity believed the universe was winding down, that gravity, patient and eternal, was gently bringing the cosmos to rest. It wasn't. It isn't. And it won't. Something else is driving now, and we're still learning its name. We drift now to the year 1998. Not so long ago in human terms, you might remember it. The internet was still finding its feet. People carried pagers and thought they were futuristic. The world seemed smaller then, more certain, more knowable. And in two separate corners of the scientific world, two teams of astronomers were about to shatter that certainty in ways they never expected. The Supernova Cosmology Project, based at Lawrence Berkeley National Laboratory, and the High Z Supernova Search Team, a rival group led by Brian Schmidt. These were not teams looking for revolution. They were looking for confirmation. They wanted to measure how quickly the universe's expansion was decelerating, not whether it was decelerating. That was taken for granted. Their tool was elegant. Type Ia supernovae. These are the deaths of particular kinds of stars, white dwarfs that have accumulated too much mass and can no longer support themselves. When they explode, they do so with remarkable consistency, almost the same brightness every time, like standardized candles scattered across the cosmos. If you know how bright something actually is, and you measure how bright it appears, you can calculate how far away it is. Simple geometry on a universal scale. By finding distant supernovae and measuring their redshift, the stretching of their light as space expands, the teams could map the history of cosmic expansion. They expected to see the supernovae slightly brighter than predicted, slightly closer, evidence that the universe had been slowing down, that gravity had been doing its job. What they found was the opposite. The distant supernovae were dimmer than expected, fainter, farther away than they should have been if the universe were decelerating. At first, both teams assumed they had made an error. Observational astronomy is difficult. Space dust can dim starlight. Instruments can be miscalibrated. Human beings make mistakes, but the data kept coming. More supernovae, more measurements, more careful corrections, and the result held. The universe wasn't just failing to slow down, it was speeding up. The expansion was accelerating. This was not supposed to happen. Nothing in the equations allowed for it. Gravity pulls things together. That's what gravity does. There was no known force that could push the universe apart on such a scale, let alone push it faster and faster as time went on. The two teams checked each other's work. They compared notes. They looked for any possible error that could explain the results away. And when they couldn't find one, they did the only honest thing scientists can do. They published. In 1998 and 1999, the papers came out. The universe was accelerating. Something was causing it, and no one had any idea what. The reaction from the scientific community was a mixture of disbelief, excitement, and a strange kind of intellectual joy. This was the best kind of discovery, one that broke everything and demanded new answers. They needed a name for this mysterious force, something that acknowledged how little they understood, something that admitted, with rare scientific humility, that they were staring into a void of ignorance. They called it dark energy. not because it was dark in color, not because it was evil or dangerous in any mythological sense, but because it was invisible, unknowable, a placeholder for something they could detect only by its effects. And in 2011, the leaders of both teams, Saul Perlmutter, Brian Schmidt, and Adam Rees, received the Nobel Prize in Physics for their accidental revolution. They set out to measure a slowdown. They discovered an acceleration, and the universe hasn't felt the same since. Let us drift a little closer now into the mechanics of the discovery, into the light of dying stars. Type Ia supernovae are among the most reliable objects in the cosmos. Not because they last long, they don't. A supernova of this type shines brilliantly for a few weeks, maybe a month, and then fades back into the darkness from which it came. But during that brief window, something remarkable happens. The explosion produces a nearly identical amount of energy every time. This consistency is rare in a universe that tends toward chaos. Stars vary wildly in size, temperature, composition. Galaxies spin at different speeds, contain different amounts of matter, live and die on different timescales. But Type Ia supernovae, for reasons rooted in the physics of white dwarfs, detonate with almost the same intrinsic brightness. This makes them what astronomers call standard candles. Imagine you're standing in a field at night and someone lights a candle a mile away. You know how bright a candle is up close, so if you see a faint flicker in the distance, you can estimate how far away it must be. The fainter the light, the greater the distance. Now imagine that same principle applied across billions of light years. You see a supernova in a distant galaxy. You know how bright Type Ia supernovae are. You measure how bright this one appears. The difference tells you the distance. But there's more. As light travels through expanding space, its wavelength stretches. Blue light becomes redder. This is called redshift, and it tells you how much space has expanded since the light was emitted. Combine distance with redshift, and you can map the history of cosmic expansion. You can see how fast the universe was expanding at different points in time. You can watch the story of the cosmos unfold backward, written in the light of ancient explosions. This is what the supernova teams were doing. They were collecting these cosmic mile markers, plotting them on graphs, building a picture of the universe's past. And the picture didn't match expectations. If the universe had been decelerating, slowing down due to gravity, the distant supernovae should have appeared closer than a simple linear model would predict. Space would have been expanding more quickly in the past, before gravity had time to slow it down. Instead, the supernovae appeared farther away. The expansion was slower in the past than it is now. Something was pushing the accelerator pedal, not the brake. The supernovae didn't lie. Stars rarely do. They simply burn and die and leave their light for us to interpret. And their light said, "The universe is not behaving the way you thought. It's running, and it's running faster." We drift backward now, through the decades, to a quieter time in physics, a time when the universe was still thought to be static, eternal, unchanging. The year is 1917. Albert Einstein has just completed his general theory of relativity, a masterpiece of human thought that describes gravity not as a force, but as the curvature of space-time itself. Mass bends space. Space tells mass how to move. It's elegant, it's revolutionary, and it has a problem. When Einstein applied his equations to the universe as a whole, they refused to stay still. General relativity predicted that the universe should be either expanding or contracting. Space couldn't just sit there, static and eternal. It had to move. But this conflicted with the prevailing wisdom of the time. Most scientists believed the universe was unchanging, had always existed, would always exist, a fixed stage on which the drama of physics played out. Einstein, despite his radical innovations, was not immune to this assumption. So he did something unusual. He added a term to his equations, a fudge factor, a mathematical constant that would provide a kind of anti-gravity, a repulsive pressure that perfectly balanced the attractive pull of matter. He called it the cosmological constant, often denoted by the Greek letter lambda. With this addition, the equations allowed for a static universe. Einstein was satisfied. The mathematics worked out. The cosmos could remain frozen in place. And then, in 1929, Edwin Hubble observed distant galaxies and discovered that they were all moving away from us. The universe was expanding after all. General relativity had been right. The cosmological constant was unnecessary. Einstein reportedly called it his greatest blunder. He had added a term to fix a problem that didn't exist, blinded by his own assumptions about how the universe should behave. The cosmological constant was removed from the equations. For decades, it gathered dust in the archives of physics history, a cautionary tale about the dangers of theoretical prejudice. And then came 1998, when the supernova teams discovered that the universe's expansion was accelerating. Physicists needed an explanation. They needed something that could push against gravity, something that could grow stronger as space expanded. And there, waiting in the mathematical archives, was Einstein's abandoned term, the cosmological constant, a repulsive pressure built into the fabric of space itself. It turned out Einstein hadn't been wrong. He had been accidentally, inexplicably right, just not in the way he intended. The cosmological constant wasn't needed to keep the universe static, but it might be exactly what was needed to explain dark energy. Today, the simplest model of dark energy treats it as a cosmological constant, a fixed energy density that permeates all of space, constant over time, causing the universe to accelerate in exactly the way observations suggest. Einstein's greatest blunder became his greatest prediction, a mistake that turned out to be a prophecy. The universe, it seems, has a sense of irony that rivals any human storyteller. Now we arrive at the heart of the mystery, the question that keeps cosmologists awake at night, that fills academic papers and fuels late-night arguments at physics conferences. What is dark energy? And here's the uncomfortable truth. We don't really know. We know what it does. We can measure its effects with extraordinary precision. We can describe its behavior mathematically. But when it comes to what dark energy actually is, what physical phenomenon it represents, we are mostly guessing. The simplest explanation, and the one that currently fits the data best, is that dark energy is a property of space itself, not something in space, not a particle floating through the void, but a characteristic of emptiness itself. Imagine empty space, truly empty, with no matter, no radiation, no particles of any kind. Classical physics would say that such a vacuum contains nothing, zero energy, pure void. But quantum physics tells a different story. At the smallest scales, empty space is seething with activity. Virtual particles pop in and out of existence, borrowing energy from the vacuum for the briefest of instants before annihilating each other. The vacuum isn't empty, it's fizzing with potential. This quantum energy of the vacuum could, in principle, act like dark energy. It would be everywhere, filling all of space uniformly. It would exert a kind of pressure, negative pressure in the language of physics, that pushes outward rather than pulling inward. And as space expands, creating more vacuum. More of this energy would appear, not because it's being created from something, but because there's simply more space for it to exist in. This is the cosmological constant model. Dark energy as vacuum energy. A fixed density of energy inherent to space itself, unchanging over time, accelerating, the expansion forever. But there's a problem, a rather significant one. When physicists try to calculate how much energy the vacuum should contain, based on quantum field theory, they get a number that is absurdly, catastrophically wrong. The prediction is off by a factor of 10^120, 10 to the 120th power. This is not a small error. This is perhaps the worst prediction in the history of science. If the vacuum energy were really that large, the universe would have torn itself apart moments after the Big Bang. Stars would never have formed. Galaxies would never have coalesced. Life would be impossible. And yet, dark energy exists. It's just much, much smaller than the equations suggest it should be. This discrepancy is called the cosmological constant problem, and it remains one of the deepest unsolved puzzles in physics. Either our understanding of quantum mechanics is fundamentally incomplete, or there's some unknown mechanism that cancels out most of the vacuum energy, leaving only a tiny residue. Or perhaps dark energy isn't vacuum energy at all. Perhaps it's something else entirely, something we haven't discovered yet, something that will require new physics to explain. For now, we call it dark energy because we don't know what else to call it. It's a placeholder for our ignorance, a name for the unnamed, and in a strange way, that's comforting. The universe still has secrets. We haven't figured everything out. There are still mysteries waiting in the dark, patient and vast, for curious minds to explore. Let's pause here for a moment and address a common misconception, a linguistic trap that catches many people when they first encounter this concept. The word dark in dark energy has nothing to do with color. It has nothing to do with evil or shadow or the absence of light in any poetic sense. It doesn't mean dark energy is hiding in black holes or lurking in the spaces between stars or somehow connected to the dark side of any cosmic force. It simply means we can't see it. In physics, dark is a confession of ignorance. It's a label we apply to things we detect through their effects, but cannot observe directly. Dark matter is matter we can't see, but whose gravitational influence we can measure. Dark energy is energy we can't see, but whose accelerating effect on the universe we can observe. The darkness is ours, not the universe's. It refers to our blindness, not to any intrinsic property of the phenomenon itself. Think of it like noticing a door swinging shut in an empty room. You didn't see anyone leave. You didn't hear footsteps. But the door moved. Something caused it. You just can't see what. That's dark energy. We see the door swinging. We see the universe accelerating, but we can't see the hand that pushed it. This is frustrating for scientists. They would much prefer to have a clear, direct detection, a particle they could capture, a wave they could measure, a signal that said, definitively, here I am. This is what I'm made of. But the universe doesn't always cooperate with our desire for clarity. Sometimes it offers only hints, shadows, effects without obvious causes. And so we work with what we have. We measure the acceleration. We calculate the energy density required to produce it. We build models and test predictions and hope that, eventually, the darkness will lift. Until then, the name remains. Dark energy, a reminder that the most powerful force in the cosmos is also the most hidden. Now, we should address a point of confusion that trips up many people, even those with a passing interest in cosmology. Dark energy and dark matter are not the same thing. They share a word, dark. But that's where the similarity ends. They are as different as fire and ice, as opposite as attraction and repulsion. Mixing them up is like confusing a magnet with a mirror, just because both start with the letter M. Dark matter pulls things together. It's a form of mass, invisible mass, undetectable by light, but mass nonetheless. We know it exists because galaxies spin faster than they should. The visible stars and gas don't have enough gravity to hold themselves together at the speeds we observe. Something else is there, adding mass, providing gravitational glue. We call it dark matter because we can't see it, but we can feel its pull. Dark energy pushes things apart. It's not mass. It's not matter. It's a form of energy, or perhaps a property of space itself, that creates a kind of anti-gravity on cosmic scales. Where dark matter gathers in clumps and helps galaxies form, dark energy stretches and separates and drives the universe apart. Together, they make up about 95% of the universe. Dark energy accounts for roughly 68%. Dark matter accounts for about 27%. And everything else, every star, every planet, every atom of your body, every photon of light, every neutrino and electron and quark, makes up the remaining 5%. We are, in cosmic terms, a rounding error. The universe is made mostly of stuff we can't see and don't understand. The visible world, the world of light and matter and experience, is the exception, not the rule. This is humbling. It's also wonderful. It means the cosmos is stranger than our senses suggest. It means there are entire categories of existence that our eyes were never designed to perceive. Dark matter and dark energy are reminders that the universe is under no obligation to be comprehensible to beings who evolved to hunt on savannas and avoid predators. We are not the measure of all things. We are explorers in a territory far larger and stranger than we ever imagined. And the exploration is only beginning. When most people imagine the universe expanding, they picture something like an explosion, a central point where the Big Bang happened. Galaxies flying outward through space like shrapnel from a bomb, spreading into some pre-existing void, filling emptiness with matter. This is intuitive. It matches our everyday experience with explosions. It feels right, and it's completely wrong. The universe is not expanding into anything. There is no pre-existing space waiting to be filled. There is no center from which galaxies are fleeing. There is no edge, no boundary, no outside where the expansion is heading. Space itself is expanding. The fabric of the cosmos is stretching. Galaxies are not moving through space. They are being carried by space as it grows. Imagine a balloon with dots drawn on its surface. As you inflate the balloon, every dot moves away from every other dot. Not because the dots are sliding across the rubber, but because the rubber itself is stretching. The distance between any two dots increases, even though neither dot is really moving. Now imagine that balloon is three-dimensional and infinite, and you're one of the dots. That's the expanding universe. From any galaxy's perspective, every other galaxy appears to be moving away. The more distant the galaxy, the faster it seems to recede. This isn't because distant galaxies are moving faster through space. It's because there's more space between you and them, and all of it is stretching. This is Hubble's law. The velocity of recession is proportional to distance. Double the distance, and the apparent velocity doubles. It's not motion in the traditional sense. It's the growth of space itself. And here's where it gets strange. If space is expanding everywhere, and the expansion is accelerating. Then there's a distance beyond which space is stretching faster than light can travel through it. Galaxies at that distance are receding from us faster than the speed of light, not because they're breaking any physical laws, but because space itself can grow at any rate it pleases. Those galaxies are beyond our reach, forever. This is the profound, unsettling implication of an accelerating universe. Not just that things are moving apart, but that the very space between them is growing faster than anything can cross it. We are becoming isolated, slowly, gently, irreversibly. Let us drift back to a simpler time when the discovery was still fresh and scientists needed metaphors to make it understandable. Edwin Hubble, the astronomer who first measured the expansion of the universe, didn't just give us a discovery. He gave us a law, a relationship so consistent that it could be expressed in a single, elegant equation. Velocity equals the Hubble constant times distance. The farther away a galaxy is, the faster it appears to recede. And the ratio, the Hubble constant, is the same everywhere in the universe. It's the rate at which space is stretching, measured in kilometers per second per megaparsec. To help people understand this, scientists developed the raisin bread model. Imagine a loaf of raisin bread, still dough, sitting in an oven. As the bread bakes, the dough rises. It expands uniformly in all directions. Now focus on one particular raisin. Call it your home raisin. As the dough expands, every other raisin moves away from you. The raisins close to you move away slowly because there's less dough between you to stretch. The raisins far from you move away quickly because there's more dough stretching. If you could measure the velocities, you'd find they follow Hubble's law. The recession speed is proportional to distance. And this is true from any raisin's perspective. Every raisin sees every other raisin moving away, as if it were the center of the expansion. But there is no center. The expansion is happening everywhere. The dough is stretching uniformly. Every point in the loaf is equivalent. This is what the universe is like. We are the raisins, space is the dough, and the baking, the expansion, never stops. Of course, the metaphor breaks down eventually. The bread has an edge, the universe might not. The bread is embedded in a kitchen. The universe isn't embedded in anything. But for grasping the basic idea, that expansion happens everywhere, that there's no center, that distance determines velocity, the raisin bread works beautifully. And now, with dark energy, the dough isn't just rising, it's rising faster and faster. The oven is getting hotter. The expansion is accelerating. The raisins are drifting apart, and they will never, ever come back together. Here is something that seems like a contradiction, but is perfectly true. The universe is getting bigger, and the observable universe is getting smaller. These two facts coexist because the observable universe is not the whole universe. It's just the part we can see, the region from which light has had time to reach us since the Big Bang. Light travels at a finite speed. The universe has a finite age. Multiply those together, and you get a distance, roughly 46 billion light years in every direction. That's the radius of the observable universe. Everything beyond that is invisible to us, not because it doesn't exist, but because its light hasn't arrived yet, or, increasingly, because it never will. Because of dark energy, space is expanding faster than light can travel through it. Galaxies that are currently near the edge of our observable universe are receding at tremendous speeds. Many of them are already moving away faster than light, and as time goes on, more and more galaxies will cross that threshold. They'll pass beyond the cosmic horizon. the boundary past which light can no longer reach us, no matter how long we wait. Once a galaxy crosses that boundary, it's gone, not destroyed, just disconnected. Its light will stretch into infinity, redshifted beyond detection, and eventually stop arriving altogether. In the far future, the observable universe will contain fewer and fewer galaxies. The night sky, if there are still beings around to look at it, will grow emptier. Stars will wink out, not because they're dying, but because they're receding beyond our ability to see. Eventually, the only galaxies visible will be those in our local group, the Milky Way, Andromeda, and a handful of smaller companions bound together by gravity. Everything else will have drifted into the unobservable dark. The universe will continue to exist. It will still be vast, still be full of galaxies and stars, and possibly life. But from our vantage point, it will appear empty. We will be alone in a way that is almost impossible to imagine. And the strangest part? Future astronomers born in that era will have no evidence that the universe was ever any different. The distant galaxies will be gone. The cosmic microwave background will be stretched to undetectability. The signs of the Big Bang, the clues to cosmic history, all of it will have faded beyond reach. They will look out at an empty sky and conclude, reasonably, that the universe has always been this way. They will be wrong, but they will never know it. Let us sit with this idea a moment longer. It deserves more than a passing mention. Right now, at this very moment, there are galaxies at the edge of the observable universe that are receding from us faster than the speed of light. This sounds impossible. Einstein said nothing can travel faster than light, and he was right. Nothing can travel through space faster than light, but space itself can expand at any rate it wants. And if the space between two objects is expanding fast enough, those objects can separate faster than light without either of them breaking any rules. Think of two people standing on a stretchy sheet of rubber. Neither of them is walking. Neither of them is moving through the rubber. But the rubber between them is stretching so fast that they're moving apart faster than either could run. That's what's happening at the edges of the cosmos. Light from those distant galaxies is still traveling toward us at the speed of light, always, faithfully, doing its best. But the space it has to cross is growing faster than it can cover. The light is on a treadmill. That's speeding up. It will never arrive. Some of that light is already on its way. Photons that left distant galaxies billions of years ago are still traveling through space, red-shifted and dim, slowly fading. Eventually, they'll be stretched so thin that they'll become undetectable. And then they'll be gone. But the galaxies themselves? They still exist. They're out there right now, full of stars and planets and possibly life. They're just unreachable, separated from us by an expanding gulf that will never close. This is the loneliness that dark energy imposes, not a dramatic catastrophe, not an explosion or a collision, just a slow, gentle, inexorable separation, a farewell that lasts forever, and we can do nothing but watch. Let us drift now into the deep future, billions of years from now, a time so distant that the sun has died, the earth has gone dark, and the Milky Way has merged with Andromeda into a single, vast, elliptical galaxy. In that future, dark energy will have done its work. Every galaxy beyond the local group will have receded past the cosmic horizon. The night sky, once filled with countless points of light, will be empty. Not dark because of clouds or dust, but dark because there is nothing left to see. The cosmic microwave background, the faint afterglow of the Big Bang, will have stretched to wavelengths so long that no instrument could detect it. The evidence for the Big Bang itself will have vanished. Future astronomers, if they exist, will look out at the universe and see nothing. Just their own galaxy, drifting alone in an infinite void. They will have no way of knowing that the universe was ever full of other galaxies. No way of knowing that the cosmos once blazed with light from horizon to horizon. They will construct theories based on what they can see. And those theories will be wrong, not because the astronomers are foolish, but because the evidence is gone. The universe will have hidden its own past. This is perhaps the most melancholy implication of dark energy. Not just that the universe is expanding, but that it's erasing its own history as it goes. Future civilizations will be born into darkness, and they will never know what they missed. We are lucky. We live in the brief window when the universe is old enough to have formed stars and planets, but young enough that distant galaxies are still visible. We can see the cosmic microwave background. We can measure the expansion. We can piece together the story of the cosmos. Future beings will not have that luxury. They will be alone in ways we can barely comprehend, and all because of dark energy, that gentle, relentless, invisible force, pushing everything apart, forever. Let us turn now to one of the most remarkable observations in all of science, a faint whisper from the beginning of time. The cosmic microwave background, or CMB, is the oldest light in the universe. It was released about 380,000 years after the Big Bang, when the cosmos cooled enough for atoms to form and light to travel freely through space for the first time. Before that moment, the universe was a hot, dense fog of plasma. Light couldn't travel far. It kept scattering off free electrons, bouncing around like a pinball in a machine. But when atoms formed, the fog cleared. Light was set free. That light has been traveling ever since. For 13.8 billion years, it has crossed the expanding universe, stretching as space stretched, cooling as the cosmos cooled. By now, it has been redshifted from visible light into microwaves, invisible to our eyes, but detectable with the right instruments. When we look at the CMB, we are seeing the universe as it was when it was only 380,000 years old, a baby universe. A universe before stars, before galaxies, before anything we would recognize. And what we see is remarkably uniform. The CMB is almost exactly the same temperature in every direction, about 2.725 Kelvin, just a few degrees above absolute zero. The universe, at that early age, was smooth and hot and simple, but not perfectly uniform. There are tiny variations, ripples in the temperature, fluctuations of a few parts per million. These variations are the seeds of everything. The slightly denser regions would eventually collapse under gravity to form galaxies. The slightly less dense regions would become the voids between them. By studying these variations, their size, their distribution, their patterns, cosmologists can learn almost everything about the universe, its age, its composition, its geometry, its fate. And the CMB tells us, with remarkable precision, that dark energy exists. The patterns we see match the predictions of a universe that is accelerating. The mathematics works. The observations confirm. The whisper from the beginning of time carries a message about its end. Let us put some numbers to this expansion, not because numbers are exciting on their own, but because they help us grasp the scale of what's happening. The current rate of cosmic expansion is measured by the Hubble constant. Its value is approximately 70 kilometers per second per megaparsec. That sounds abstract, so let's translate. A megaparsec is about 3.26 million light years. For every megaparsec of distance between two objects, space is stretching by 70 kilometers every second. If you're 1 megaparsec away from a galaxy, that galaxy appears to be receding at 70 kilometers per second. If you're 2 megaparsecs away, it's receding at 140 kilometers per second. If you're 100 megaparsecs away, it's receding at 7,000 kilometers per second. And if you're far enough away, about 4,200 megaparsecs, the recession velocity exceeds the speed of light. Beyond that distance, galaxies are moving away faster than light itself can travel. That distance, the Hubble radius, is the boundary of our cosmic neighborhood. Everything beyond it is receding superluminally. And because of dark energy, that boundary is shrinking in a sense. More and more galaxies are crossing it every moment. Now 70 kilometers per second per megaparsec doesn't sound like much. It's a slow stretch in human terms. You wouldn't notice it in your living room, or your city, or your solar system. On small scales, gravity overwhelms the expansion easily. But on cosmic scales, over billions of years, this gentle stretch adds up. Distances double. Galaxies that were once close become distant. Galaxies that were distant become unreachable. Dark energy is patient. It doesn't need to rush. It has all the time in the universe. And the expansion continues. Here's a curious puzzle, one that keeps cosmologists busy and slightly worried. Different methods of measuring the Hubble constant give slightly different answers. If you measure the expansion using the cosmic microwave background, looking at the early universe and calculating how fast it should be expanding today, you get a value around 67 kilometers per second per megaparsec. If you measure the expansion using local observations, like type Ia supernovae in nearby galaxies, you get a value around 73 kilometers per second per megaparsec. That's a difference of about 9%, which doesn't sound like much, but in precision cosmology, it's enormous. The measurements are too precise to be that far apart by chance. This discrepancy is called the Hubble tension, and it's become one of the most discussed problems in modern cosmology. Maybe it's an error. Maybe one of the methods is systematically wrong. Maybe there's a calibration issue or a dust problem or a statistical fluke. Scientists are working hard to check and recheck the data. But maybe, and this is the exciting possibility, maybe both measurements are correct. Maybe the universe isn't behaving the way our models predict. Maybe dark energy isn't constant after all. Maybe it's changing over time. Maybe there's new physics lurking in the gap. If dark energy is evolving, growing stronger or weaker, it could explain the discrepancy. The early universe and the late universe would have experienced different expansion rates, and the tension would make sense. Or maybe there's something else entirely. A new particle, a new force, a revision to general relativity, something we haven't thought of yet. The Hubble tension is a reminder that our understanding of dark energy is incomplete. We have models, but models aren't truth. They're approximations, waiting to be improved or replaced. And in that tension, in that gap between measurements, the next great discovery might be hiding. Let us drift now into the far future, not millions of years, but trillions, quadrillions, numbers so large they stop meaning anything. If dark energy continues as it is, constant, unchanging, forever pushing, the universe will end in heat death. This is not a dramatic end. There is no explosion, no collapse, no final moment of cosmic drama. It's quieter than that, sadder in a way. Stars will continue to form for a while, but eventually the raw materials will run out. The gas and dust needed to make new stars will be used up or scattered. The last stars will ignite, burn through their fuel, and die. White dwarfs will cool. Neutron stars will spin down. Black holes will linger, but even they are not eternal. Through a process called Hawking radiation, black holes slowly evaporate, losing mass over inconceivable timescales. Eventually, even the largest black holes will fade away. What remains? Empty space, cold, dark, and featureless. A few stray particles drifting aimlessly, the temperature approaching absolute zero. Nothing happening, nothing changing, no energy flowing from place to place. This is maximum entropy, the state where everything is evenly distributed and nothing can happen. The universe has reached thermodynamic equilibrium. It's not dead in the sense of being destroyed. It's dead in the sense of being done. Nothing left to do. No more stories to tell. This is the heat death of the universe. Not a bang, but a whimper. Not fire, but ice. And dark energy, by accelerating the expansion, hastens this end. It stretches the cosmos thinner and thinner, pushing everything apart, ensuring that the heat death is deep and complete and forever. It's a melancholy vision, but there's a strange peace in it too. The universe will have run its course. Every star that ever burned, every planet that ever turned, every thought that ever flickered in a conscious mind, all of it will have been part of a vast, temporary experiment in existence. And then, stillness. Now, we drift toward a darker possibility, a future that doesn't whisper, but tears. For most of this journey, we've spoken of endings that feel almost peaceful. The heat death of the universe, with its slow fade into cold equilibrium, the gradual dimming of stars, the quiet evaporation of black holes across timescales so vast they make human history look like a single heartbeat. These endings, while melancholic, carry a certain dignity. A universe that simply runs out of energy, like a campfire burning down to embers, is sad, but not violent. But there's another possibility, one that physicists take seriously, one that ends not with a whisper, but with the most catastrophic event imaginable. It's called the Big Rip, and it begins with a simple question. What if dark energy doesn't stay constant? You see, in all our previous discussions, we've treated dark energy as a fixed property of space, a cosmological constant, just as Einstein once imagined. The same pressure, everywhere, always, steady and unchanging across billions of years. And if that's true, the universe will expand forever, but it will never expand violently. Galaxies will drift apart. The sky will empty, but the fabric of space itself will remain intact. The Big Rip scenario imagines something different. What if dark energy grows stronger over time? Not just a little stronger, not a gentle increase, but an accelerating increase. A runaway effect where the expansion of space doesn't just continue, but compounds. Where the rate of acceleration itself accelerates. Where the pressure pushing the universe apart becomes more intense with every passing moment. If this happens, the consequences are difficult to comprehend. At first, the changes would be subtle. Galaxies that were already drifting away would drift faster. The cosmic horizon, the boundary beyond which light can never reach us, would shrink more rapidly. Distant clusters would vanish from view, not over billions of years, but over millions, then thousands, then less. But the truly terrifying part comes later, because if dark energy strengthens without limit, it won't just push galaxies apart, it will push everything apart. Think about what holds a galaxy together. Gravity, the mutual attraction of billions of stars, pulling toward a common center. Under normal conditions, even with dark energy as it currently exists, gravity wins on galactic scales. The Milky Way stays bound. Andromeda stays bound. Galaxy clusters hold together more or less. even as the space between clusters expands. But in the Big Rip scenario, dark energy eventually overpowers gravity. First, galaxy clusters tear apart. The gravitational bonds that held them together for billions of years simply cannot compete with the growing pressure of expanding space. Clusters dissolve. Galaxies that once orbited each other now fly apart, never to meet again. Then, individual galaxies tear apart. The Milky Way, our home for the past 13 billion years, would begin to unravel. Stars that once orbited the galactic center would find themselves drifting outward, as if gravity itself had forgotten how to work. The spiral arms would stretch, the core would disperse. Within a cosmically short time, perhaps millions of years, perhaps less, the galaxy would cease to exist as a coherent structure. But it doesn't stop there. Next, solar systems tear apart. Our sun, if it still existed, would lose its grip on its planets. Earth would drift away from its star, not because of any orbital decay, but because the space between them was stretching faster than gravity could compensate. The moon would leave Earth. Moons would leave their planets. Every gravitational relationship in the solar system would dissolve one by one as the expansion of space overwhelmed every force trying to hold things together. And still, it doesn't stop, because after solar systems come planets. In the final stages of the Big Rip, the expansion of space would become so violent that it would tear apart solid objects, not just push them apart, tear them apart. The forces holding molecules together, the forces holding atoms together, would be overcome by the sheer pressure of expanding space. Planets would shatter, not from collision, not from explosion, but from the fabric of reality itself, stretching faster than matter can hold. Imagine standing on Earth in those final moments, if such a thing were possible. The ground beneath you wouldn't crack from an earthquake. It would simply expand. The distance between atoms would grow. Solid rock would become less solid, less coherent, less real. And then, in the final instance, even atoms would tear apart. Electrons would be ripped from their nuclei. Protons and neutrons would separate. Quarks, the fundamental building blocks of matter, would be pulled apart by the expansion of space itself. And in that moment, matter as we know it would cease to exist. This is the Big Rip. The universe doesn't fade, it doesn't cool, it doesn't quietly expire. It shreds itself into nothingness, torn apart by the very force that once gently pushed galaxies away from each other. The timeline depends on how quickly dark energy strengthens. Some models suggest the Big Rip could occur in as little as 22 billion years. That sounds like a long time, and it is. But compared to the heat death scenario, which unfolds over timescales of 10 and 100 years and beyond, it's practically tomorrow. Now, here's the comforting part. We don't know if this will happen. The Big Rip is a possibility, not a certainty. It requires a specific kind of dark energy, one with what physicists call a phantom equation of state. Current observations suggest dark energy is probably constant or very close to it. The Big Rip remains theoretical, a mathematical possibility that we cannot yet rule out, but also cannot yet confirm. So as you lie there, feeling the solid bed beneath you, the stable floor beneath that, the quiet earth beneath that, you can take comfort in knowing that the forces holding you together are, for now, far stronger than anything trying to pull you apart. The universe may have a violent end waiting billions of years in the future, or it may simply fade into silence. Either way, tonight, you are held, you are whole, and the atoms that make you are content to stay exactly where they are. Let that thought settle over you like a blanket, heavy, warm, unmoving. And slowly, we drift onward. Now we move to the very edge of what physics can describe, the place where equations strain, where predictions become guesses, where the universe whispers possibilities that make even cosmologists uneasy. We enter the realm of phantom energy. In our previous segment, we explored the Big Rip, the scenario where dark energy strengthens over time and eventually tears apart everything from galaxies to atoms. But we didn't fully explain what kind of dark energy would be required for such a catastrophic end. That's where phantom energy comes in. To understand phantom energy, you first need to understand how physicists describe dark energy mathematically. They use something called the equation of state parameter, which is represented by the letter W. This parameter describes the relationship between pressure and density for any component of the universe. For ordinary matter, the stuff that makes up stars, planets, and people, W equals 0. Matter just sits there. It has density, but no pressure that affects the expansion of space. For radiation, light, heat, electromagnetic energy, W equals 1/3. Radiation exerts a small amount of pressure, which is why a flashlight pointed at a piece of foil can, in principle, push it ever so slightly. For dark energy as a cosmological constant, the version Einstein proposed, and the version most consistent with current observations, W equals -1. This means dark energy has negative pressure. It doesn't push things together, it pushes them apart. And crucially, its density remains constant even as space expands. No matter how much the universe grows, there's always the same amount of dark energy per cubic meter. This is strange, this is counterintuitive, but it's what the data suggests. Phantom energy is what happens when W is less than -1. Think about that for a moment. If dark energy with W equals -1 creates a universe that expands forever at an accelerating rate, what does it mean for W to be even more negative? What does it mean for the pressure to be even more extreme? It means the density of dark energy increases as space expands. Let that sink in. With a cosmological constant, dark energy density stays the same. With phantom energy, it grows. The more the universe expands, the more dark energy there is per unit volume. The more dark energy there is, the faster expansion accelerates. The faster expansion accelerates, the more space is created, and the more space is created, the more phantom energy appears. It's a runaway feedback loop with no natural stopping point. This is what leads to the Big Rip. Not just dark energy pushing things apart, but dark energy that grows stronger with every passing moment, feeding on the very expansion it creates, until the pressure becomes infinite and the universe tears itself apart in a finite amount of time. Now, here's where theory gets uncomfortable. Phantom energy, if it exists, violates some of the basic principles that physicists rely on to make sense of the universe. It violates something called the dominant energy condition, which essentially says that energy can't flow faster than light. Phantom energy would allow for superluminal energy transfer, which opens up all sorts of paradoxes and problems. It may also violate the null energy condition, which is even more fundamental. Violating this condition would have bizarre implications for the nature of space-time, potentially allowing for things like traversable wormholes or closed time-like curves, paths through space-time that loop back to their own past. In other words, phantom energy doesn't just predict a violent end to the universe. It predicts a universe where the rules we thought we understood start to break down. Most physicists are skeptical that phantom energy exists. The simplest explanation for dark energy, a cosmological constant with W exactly equal to -1, fits the data reasonably well. Current measurements of W hover around -1 with some uncertainty. If the true value is exactly -1, There's no phantom energy and no big rip. If it's even slightly less than -1, the implications are profound. So we measure, we observe, we refine our instruments and extend our surveys, trying to pin down the value of W to more and more decimal places. The answer matters. If W equals -1, the universe has a cold but stable future, eternal expansion into emptiness, a slow fade rather than a violent end. If W is less than -1, even by a small amount, the universe has a deadline. A moment, billions of years from now, when the fabric of space can no longer hold itself together. When expansion goes from gradual to catastrophic. When everything ends not with a whimper, but with a rip. As you lie there, breathing slowly, you can take comfort in the fact that current evidence slightly favors the gentler option. The universe, as far as we can tell, is probably not tearing itself apart. Probably. But the uncertainty remains. The measurements aren't perfect. And somewhere in that uncertainty lies the possibility of phantom energy, a force so extreme, so self-reinforcing, that it would eventually destroy not just everything we know, but space-time itself. It's the kind of thought that could keep you awake, if you let it. So don't let it. Instead, let it remind you how remarkable it is that we can even ask these questions, that creatures made of atoms, living on a small planet, orbiting an ordinary star, can measure the expansion of the universe and wonder about its ultimate fate. That we can sit at the edge of human knowledge and peer into the darkness, searching for answers that may take centuries to find. The universe may have terrifying possibilities written into its equations, but tonight, none of them matter. Tonight, you are here. You are safe. And the phantom, if it exists at all, is very, very far away. Now we arrive at something extraordinary, not because it's elegant, but because it's embarrassing. This is the cosmological constant problem, and it represents, without exaggeration, the worst prediction in the entire history of physics. Let's set the stage. You've learned that dark energy behaves like a cosmological constant, a fixed energy density that pervades all of space and causes the universe to expand at an accelerating rate. This energy exists in every cubic meter of vacuum. It's there between galaxies. It's there between stars. It's there in the empty space between the molecules in your body right now. The amount is tiny, roughly 6x 10 to 10 joules per cubic meter. That's an almost inconceivably small number. To put it in perspective, the energy contained in a single raisin, if converted to vacuum energy at this density, would fill a volume of space roughly the size of the Earth. So, dark energy is real but extremely weak. It only becomes significant on the largest scales, across billions of light years, where its cumulative effect overwhelms gravity. Now, here's where the problem begins. Quantum mechanics, the theory that describes the behavior of particles at the smallest scales, predicts that empty space should not be empty at all. Even in a perfect vacuum, with no particles, no light, no matter of any kind, there should still be energy. This is called vacuum energy, or zero-point energy. The reason is subtle but well established. Quantum mechanics tells us that particles are constantly popping in and out of existence. Virtual particles that appear, exist for an unimaginably brief moment, and then vanish. This constant quantum activity gives the vacuum a kind of background energy, a baseline hum of existence that can never be completely eliminated. When physicists calculate how much vacuum energy should exist based on quantum mechanics, they get a number. And the number is absolutely enormous. The predicted vacuum energy density using straightforward quantum field theory is roughly 10 to 113 joules per cubic meter. That's a 1 followed by 113 zeros. Compare that to the observed value of dark energy, roughly 10 joules per cubic meter. The difference between the predicted and observed values is a factor of 10 123 orders of magnitude. This is not a small discrepancy. This is not a rounding error. This is a disagreement so vast, so absurd, so catastrophic that it makes every other failed prediction in physics look like a minor inconvenience. To put this in perspective, if your weather forecast predicted a temperature of 70 degrees Fahrenheit and the actual temperature was 70 trillion degrees, you would not say the forecast was close. You would say something had gone terribly, fundamentally wrong with your model of how temperature works. That's the cosmological constant problem. The laws of physics, as we currently understand them, predict that the vacuum should have so much energy that the universe would have torn itself apart immediately after the Big Bang. Space would have expanded so violently, so instantly, that no structures could ever form, no galaxies, no stars, no planets, no atoms, no you. And yet, here we are. The universe exists. It expanded at a reasonable rate. Structures formed, life emerged. You're lying in bed right now, breathing, thinking, existing, despite the fact that our best theories say this should be impossible. So what went wrong? The honest answer is, we don't know. This is not a small gap in our understanding. This is a gaping chasm at the heart of modern physics. Two of our most successful theories, quantum mechanics and general relativity, are both well-tested and extremely reliable in their own domains. Quantum mechanics predicts the behavior of particles with extraordinary precision. General relativity predicts the behavior of space-time, gravity, and the cosmos with equal success. But when we combine them to predict the energy of empty space, we get nonsense. We get a number so wrong that it embarrasses everyone who thinks about it. Several solutions have been proposed, but none are satisfying. Some physicists suggest that there's some unknown mechanism that cancels out most of the vacuum energy, leaving only the tiny residual that we observe as dark energy. But no one has found this mechanism, and the cancellation would have to be precise to 123 decimal places, an almost miraculous fine-tuning. Others invoke the anthropic principle, arguing that we only observe a universe with small vacuum energy because universes with large vacuum energy can't support life. In a multiverse of many possible universes with different physical constants, we inevitably find ourselves in one where the constants allow existence. This explanation is controversial because it seems to give up on finding a deeper reason. It's explanation by selection rather than explanation by mechanism. Still, others suggest that our understanding of quantum field theory breaks down in ways we haven't yet grasped. Perhaps the calculation itself is flawed. Perhaps vacuum energy doesn't gravitate the way we assume. Perhaps there's something fundamentally wrong with how we apply quantum mechanics to the cosmos. The truth is, the cosmological constant problem remains unsolved. It hangs over physics like a cloud, reminding us that despite all our progress, despite all our beautiful equations and precise measurements, there are things we simply do not understand. And perhaps there's something comforting in that. The universe is not fully explained. The mystery is not solved. The book is not finished. And in that incompleteness, there's room for wonder, room for future discoveries, future insights, future moments when someone finally figures out what we've been missing. Tonight, as you drift towards sleep, let the cosmological constant problem be a reminder that even the most confident-seeming knowledge has edges, that even the smartest people in history have stood before the universe and admitted they don't understand. You're in good company. The universe is strange, and it's okay to not have all the answers. Now we venture into speculation, carefully, gently, with the humility of explorers who know they might be wrong. For most of this journey, we've treated dark energy as if we understand it. We've given it a name. We've described its effects. We've traced its influence across billions of light years and billions of years. We've even discussed its possible futures: heat death, big rip, phantom scenarios. But here's the truth. We don't know what dark energy is. Not really. We know what it does. We know that something is causing the universe to expand at an accelerating rate. We can measure this acceleration with precision. We can model it mathematically. We can make predictions based on our observations. But the thing itself, the actual nature of dark energy, remains almost entirely unknown. And some physicists wonder if we've been looking at this wrong all along. What if dark energy isn't a substance at all? What if it's not a field, not a constant, not a form of energy in the traditional sense? What if dark energy is a sign that our theory of gravity is incomplete? This is a radical idea, but it's not crazy. General relativity, Einstein's theory of gravity, has been extraordinarily successful. It predicts the orbits of planets, the bending of light around massive objects, the existence of black holes, the behavior of gravitational waves. Every test we've thrown at it, it has passed. But every test we've conducted has been on relatively small scales. The solar system, neutron stars, black hole mergers, even galaxy-scale observations, while larger, are still tiny compared to the size of the entire cosmos. What if general relativity breaks down on the largest scales? Several modified gravity theories have been proposed over the years. Some add new terms to Einstein's equations. Some introduce additional fields that only become relevant at cosmic distances. Some change the fundamental relationship between matter and space-time. The most famous of these is called MOND, Modified Newtonian Dynamics, which was originally developed to explain the rotation curves of galaxies without invoking dark matter. MOND suggests that gravity behaves differently at very low accelerations than Newton or Einstein predicted. If MOND, or a similar theory, could explain both dark matter and dark energy as artifacts of incomplete gravitational theory, it would revolutionize physics. It would mean that two of the biggest mysteries in cosmology, the invisible mass holding galaxies together and the invisible pressure pushing them apart, are not mysteries at all, but consequences of our misunderstanding of gravity. Unfortunately, modified gravity theories have struggled to match the full range of observations. While they can explain some phenomena, they often fail to explain others. And the data from the cosmic microwave background, from galaxy surveys, from gravitational lensing, all seem to favor the existence of actual dark matter and dark energy as real components of the universe, not illusions created by modified physics. But the door isn't closed. New theories continue to be developed. New observations continue to refine our understanding. And the possibility remains that one day, someone will propose a theory of gravity that naturally explains the accelerating expansion of the universe without needing to invoke a mysterious dark energy at all. There's another possibility, equally speculative. What if dark energy is evidence of extra dimensions? String theory, which attempts to unify all the forces of nature into a single mathematical framework, requires the existence of additional spatial dimensions beyond the three we experience. These extra dimensions would be too small to detect directly, curled up at scales far smaller than atoms. But some versions of string theory suggest that gravity can leak into these extra dimensions, which would weaken it at large distances. If gravity is weaker than we think on cosmic scales, it might appear as if something is pushing the universe apart, when really, gravity is just not pulling as hard as we expected. This is highly speculative. There's no direct evidence for extra dimensions, and making string theory produce specific, testable predictions for dark energy has proven extremely difficult. But the possibility exists. In the vast landscape of theoretical physics, dark energy might turn out to be a clue, a hint pointing toward a deeper truth about the nature of space, time, and reality itself. There's yet another possibility, one that borders on the philosophical. What if dark energy is something so fundamentally new that we don't have the concepts to describe it yet? Throughout the history of science, there have been moments when existing ideas simply weren't adequate to explain new observations. When Newtonian mechanics couldn't explain the orbit of Mercury, when classical physics couldn't explain black-body radiation, when existing theories of light couldn't account for the photoelectric effect. Each time, the solution required not just new equations, but new concepts, new ways of thinking about reality, space-time, quanta, wave-particle duality. Perhaps dark energy is one of those moments. Perhaps it's pointing toward a concept we haven't invented yet, a feature of the universe so strange, so unlike anything we've encountered, that our current theories can only gesture at it without truly grasping it. If that's the case, then dark energy is not just a mystery. It's an invitation, a door that, when opened, will reveal something we never expected. And perhaps the next Einstein, the next Bohr, the next Planck is out there right now, maybe even listening to this, waiting to have the insight that changes everything. For tonight, though, the mystery remains. Dark energy is real. Its effects are measurable. Its nature is unknown. And in that unknown, there is room for dreams. Now we turn to an idea that carries an ancient name and a modern mystery: quintessence. The word comes from Aristotle, who believed that while the earth was made of 4 elements, earth, water, air, and fire, the heavens were composed of a 5th element, a perfect and unchanging substance that filled the celestial spheres. He called it ether, or quintessence, from the Latin quinta essentia, meaning 5th essence. For centuries, philosophers and scientists speculated about this mysterious 5th element. Was it real? Was it detectable? Did it permeate all of space? In the 20th century, the idea of a universal ether was abandoned. Einstein's relativity showed that space didn't need a medium for light to travel through. The classical ether was consigned to history. But in the late 1990s, when astronomers discovered that the universe was expanding at an accelerating rate, some physicists reached back to that ancient concept. Not because Aristotle was right, but because they needed a name for something new, something that filled all of space, something that might change over time. They called it quintessence. Modern quintessence is not Aristotle's perfect heavenly substance. It's a hypothetical field, like an electromagnetic field or a gravitational field, that pervades all of space and exerts a negative pressure, causing the universe to expand at an accelerating rate. The key difference between quintessence and a cosmological constant is simple but profound. Quintessence can change. A cosmological constant, by definition, is constant. It has the same value everywhere in space and at every moment in time. It was the same at the Big Bang as it is now, and it will be the same in 1 trillion years. Quintessence, on the other hand, is dynamic. Its energy density can evolve. It can be stronger at some times and weaker at others. It might have started with one value in the early universe and gradually changed to a different value today. This has important implications. If dark energy is a cosmological constant, then the fate of the universe is largely determined. We can calculate how fast expansion will accelerate and what the ultimate end will look like. Heat death, probably. An eternal, empty, cold cosmos. But if dark energy is quintessence, the future is less certain. The field might strengthen, leading to something like the Big Rip. It might weaken, allowing gravity to eventually dominate again. It might even reverse sign, changing from repulsive to attractive, potentially causing the universe to collapse in a big crunch. Quintessence opens up possibilities that a cosmological constant forecloses. Several theoretical models for quintessence have been proposed. Most involve a scalar field, a field that has a value at every point in space, but no direction, unlike electric or magnetic fields which point somewhere. The scalar field slowly rolls down a potential energy curve, like a ball rolling down a very gentle hill. The speed and shape of this roll determine how dark energy evolves over time. Some models predict that quintessence was much stronger in the early universe, driving an initial period of rapid expansion before settling into its current, gentler acceleration. Others predict that quintessence is strengthening, slowly building toward a future crisis. Still others suggest oscillations, with dark energy periodically rising and falling over billions of years. The challenge is distinguishing quintessence from a cosmological constant observationally. If dark energy is evolving, it should leave fingerprints in the data. The rate of cosmic expansion should change in specific ways depending on how the quintessence field behaves. The growth of cosmic structures, galaxies, clusters, superclusters, should be affected. The cosmic microwave background should carry subtle signatures of a dynamic dark energy. Astronomers are looking for these signatures. Surveys like the Dark Energy Survey, the Euclid mission, and the Vera Rubin Observatory's Legacy Survey of Space and Time are mapping the universe with unprecedented precision, hoping to detect even tiny deviations from what a cosmological constant would predict. So far, the data is consistent with a cosmological constant. Dark energy appears to be unchanging, within the limits of our measurement precision. But those limits are still fairly wide. There's room for quintessence to hide. And if it's found, if we detect that dark energy is indeed changing over time, it would transform our understanding of the universe. It would mean that the force driving cosmic acceleration is not a fixed property of space, but a living, evolving field with its own dynamics and its own history. There's something almost poetic about that possibility. The universe would not just be expanding, it would be changing in ways we can't fully predict. The future would be genuinely open, contingent on the behavior of a field we barely understand. Tonight, as you lie in the darkness, you might imagine quintessence as a kind of cosmic breath, inhaling and exhaling across billions of years. The universe not as a machine running down, but as something more organic, something that pulses, something that evolves. Of course, this is speculation. Quintessence may not exist at all. The cosmological constant may be exactly that, constant. The universe may be simpler than our theories allow, but the possibility of quintessence reminds us that even our best understanding is provisional, that the universe may yet surprise us, that the story of dark energy is not yet complete. And in that incompleteness, there is room for wonder, for curiosity, for the kind of quiet awe that settles over you like sleep, gentle and inevitable. Now we turn the clock backward, not to the beginning of time, but to a transition, a moment when the universe shifted from one era to another, a quiet revolution that changed everything. For most of the universe's history, dark energy didn't matter. Let that sink in for a moment. The force that now drives the accelerating expansion of the cosmos, the entity that constitutes 68% of all that exists, was once irrelevant. A footnote, a whisper so faint that gravity drowned it out entirely. To understand why, you need to understand how the different components of the universe behave as space expands. Matter, the stuff that makes up stars, planets, galaxies, and you, dilutes as the universe grows. Imagine a box full of marbles. If you make the box bigger, the marbles spread out. The number of marbles per cubic meter decreases. The density of matter drops as the volume of space increases. Radiation, light, heat, neutrinos, anything moving at or near the speed of light, dilutes even faster. Not only does radiation spread out as space expands, but each individual particle of radiation also loses energy. The wavelength of light stretches as space stretches, shifting from blue to red, from visible to infrared, from infrared to microwave. This is called redshift. It means that radiation becomes both less dense and less energetic as the universe expands. Dark energy, by contrast, doesn't dilute at all. If dark energy is a cosmological constant, as current evidence suggests, then its density remains fixed no matter how much space expands. 1 cubic meter of vacuum has the same dark energy now as it did 1 billion years ago, and the same as it will have 1 billion years from now. This leads to a profound consequence. In the early universe, when everything was packed together, the density of matter and radiation was enormous. Space was filled with hot, dense plasma. Light couldn't travel more than a tiny distance before colliding with a charged particle. The universe was opaque, violent, and dominated by radiation. Back then, dark energy was insignificant. Its constant density was vastly outweighed by the overwhelming density of matter and radiation. It existed presumably, but it had no influence on the evolution of the cosmos. Gravity ruled, matter clumped, radiation flowed, dark energy waited. As the universe expanded, radiation diluted and cooled. Eventually, matter took over as the dominant component. This happened about 47,000 years after the Big Bang, at a moment called matter-radiation equality. From that point on, gravity shaped the cosmos. Clouds of dark matter collapsed. Galaxies formed. Stars ignited. The universe we recognize began to take shape. But all this time, dark energy was patient. As space continued to expand, the density of matter kept dropping. Galaxies spread out. The average density of the universe fell lower and lower, and at some point, the constant density of dark energy began to rival, then match, then exceed the declining density of matter. This transition happened roughly 5 billion years ago. Think about that. 5 billion years ago, our sun was just beginning to form from a collapsing cloud of gas and dust. The Earth didn't exist yet. Life was nowhere to be found. And at that same moment, on the largest scales, the universe was undergoing a fundamental shift in its behavior. Before 5 billion years ago, the expansion of the universe was decelerating. Gravity was winning. The mutual attraction of all the matter in the cosmos was slowing down the expansion, fighting against the initial push of the Big Bang. If this had continued indefinitely, the universe might have eventually stopped expanding and begun to contract. But 5 billion years ago, dark energy took over. As matter diluted and dark energy remained constant, the balance tipped. The repulsive pressure of dark energy began to outweigh the attractive pull of gravity. The expansion of the universe stopped slowing down and started speeding up. This was the dawn of the dark energy era. We are now living deep inside this era. Dark energy has been dominant for billions of years, and it will remain dominant for the foreseeable future. As the universe continues to expand, matter will dilute further, and dark energy's dominance will only increase. In a sense, we are witnesses to a cosmic changing of the guard. For most of the universe's history, gravity shaped the story. Matter collapsed, structures formed, complexity grew. But that era is ending in a cosmic sense. The age of structure formation is giving way to the age of dissolution. Dark energy is slowly pulling the universe apart, erasing the connections between galaxies, dimming the sky, and steering the cosmos toward an empty, cold, and silent future. We are alive at the transition. Behind us lies the era of matter, with its stars and galaxies and possibilities. Ahead lies the era of dark energy, with its emptiness and expansion and eternal cold. And here, in this brief moment, we exist. We look back and understand the past. We look forward and glimpse the future. We are the universe becoming aware of itself, just as it crosses the threshold between one age and another. There's something melancholy about that, but also something beautiful. You are here now, in the only moment that is truly yours. The past is gone. The future is uncertain. But tonight, you rest in the present, a thin line between what was and what will be. Let that thought carry you gently forward, into sleep, into dreams, into whatever comes next. Now we come to a puzzle that might have been bothering you all along. If dark energy is everywhere, if it fills every cubic meter of space, including the space inside your body, inside your room, inside the very atoms that make up your being, why can't you feel it? Why doesn't it push your cells apart? Why doesn't it stretch the distance between your heart and your lungs? Why doesn't it affect the air you breathe, the bed you're lying on, the planet beneath you? The answer reveals something important about how the universe works, something subtle, something almost counterintuitive. Dark energy is everywhere, but it's weak, extraordinarily, almost absurdly weak. Remember the number, roughly 6 × 1010 joules per cubic meter. That's the energy density of dark energy. It's so small that in everyday contexts, it's utterly meaningless. To put this in perspective, the air in your room has an energy density, just from the random motion of molecules, that's billions of times higher than dark energy. The gravitational binding energy of the Earth is incomparably greater. Even the faint electromagnetic attraction between the molecules in your skin dwarfs the effect of dark energy on those same molecules. Dark energy is the weakest force on small scales. On the scale of atoms, the electromagnetic force dominates. It holds electrons to nuclei. It binds molecules together. It makes chemistry possible. On the scale of planets and stars, gravity dominates. It holds the Earth together. It keeps the moon in orbit. It makes the sun shine. On the scale of galaxies, gravity still dominates, aided by dark matter, which provides extra mass to hold things together. Dark energy can't compete with any of these forces on their home turf. It's simply too weak. But here's the key insight. Dark energy is cumulative. On small scales, its effect is negligible, completely overwhelmed by stronger forces. But on very large scales, across hundreds of millions of light years, dark energy adds up. There's no counteracting force. Gravity falls off with distance. Electromagnetism is shielded and neutralized. But dark energy just keeps accumulating, steadily pushing every region of space slightly away from every other region. It's like inflation in economics. A 2% inflation rate doesn't affect your daily coffee purchase in any noticeable way, but over decades, it transforms the entire economy. Prices that seemed fixed gradually double, triple, change beyond recognition. Dark energy is the cosmic equivalent. On small scales, undetectable. On vast scales, dominant. This is why you can't feel dark energy in your daily life. The distance between your hands, maybe half a meter, has dark energy filling it. But the expansion it causes is so infinitesimally small that it's completely unmeasurable. The gravitational attraction between your hands, weak as it is still billions of times stronger than the dark energy repulsion. Even the distance between the Earth and the Sun is too small for dark energy to matter. The gravitational binding of the solar system is vastly stronger than any expansion effect. The planets will stay in their orbits for as long as the sun shines, unaffected by dark energy's gentle push. Even the Milky Way galaxy is too small. Gravity holds our galaxy together with ease. Dark energy has no influence on our local group of galaxies, which will remain gravitationally bound for the foreseeable future. It's only when you zoom out to the scale of galaxy clusters and beyond, tens of millions of light years, that dark energy starts to matter. At those distances, the gravitational binding between structures becomes weak enough that dark energy's cumulative effect takes over. Clusters that aren't already bound together will never become bound. They'll drift apart, accelerating into the darkness. So you can't feel dark energy because you're too small, and the things around you are too close together. But that doesn't mean it's not there. Right now, as you lie in bed, dark energy fills the space around you. It's in the gap between your pillow and your cheek. It's in the air you breathe. It's in the empty space between atoms and every molecule of your body. It's just too weak to matter. But zoom out far enough, far beyond your room, your city, your planet, your star, your galaxy. And dark energy is the most powerful force in the universe. Not because it's strong, but because it never gives up. It never weakens. It just keeps pushing, gently, patiently, relentlessly. There's something almost zen about that. The weakest force, applied everywhere forever, eventually wins. Not through violence, not through explosions or collisions or dramatic events, just through quiet, constant persistence. As you drift towards sleep, let that be a thought to hold on to. Not every force needs to be strong to matter. Sometimes, the gentlest push, sustained long enough, changes everything. Now we arrive at something deeply personal, a reflection not on the cosmos, but on us, on you, on the strange, improbable privilege of being alive right now. You exist in a particular moment in cosmic history, not just any moment, a remarkable one. The universe is roughly 13.8 billion years old. In that vast span of time, countless eras have come and gone. The first fraction of a second saw the birth of space and time, the emergence of fundamental forces, the creation of matter itself. The first few 100,000 years were a hot, opaque plasma with no stars, no galaxies, no structures of any kind. Then came the Dark Ages, hundreds of millions of years when the universe was cold, empty, and silent, waiting for the first stars to ignite. Then came the age of star formation. Galaxies assembled. Heavy elements were forged in stellar cores and scattered by supernovae. Planets formed. Chemistry grew complex. And somewhere, on at least one unremarkable planet orbiting an unremarkable star, life emerged. That's where you are. That's when you are. But here's what makes your moment special. You are alive during the only window in cosmic history when the universe is both interesting and comprehensible. In the distant past, the universe was too hot and chaotic for complex structures to exist. In the distant future, the universe will be too empty and cold for anything to happen. But right now, in this cosmic eye blink called the present, the universe is just right. Cool enough for atoms to form molecules, dense enough for stars to ignite, complex enough for life to emerge, and still young enough for distant galaxies to be visible. Consider that last point. Right now, we can see galaxies billions of light years away. We can measure the cosmic microwave background, the faint afterglow of the Big Bang, and reconstruct the history of the universe from its earliest moments. We can observe the expansion of space and infer the existence of dark matter and dark energy. This will not always be true. In the far future, trillions of years from now, the accelerating expansion of the universe will push nearly all galaxies beyond the cosmic horizon. Their light will be stretched to invisibility. Their signals will never reach whatever observers remain. Future astronomers, if they exist, will look out at the sky and see nothing. Just their own galaxy, isolated in an infinite void. They will have no evidence that the universe was ever different, no way to know that billions of galaxies once filled the sky, no means to discover the cosmic microwave background, which will have been redshifted into oblivion. They will live in a universe that appears static, eternal, and alone. They will be wrong, of course. The universe will still have a history. It will still have expanded from a hot, dense state. Dark energy will still be driving acceleration, but they won't know any of this. The evidence will be gone. The story will be erased. You, however, are alive before the erasure. You exist in the window when the universe reveals its secrets, when the evidence is still visible, when the story can still be told. This is not a coincidence of physics. It's a consequence of it. Complex life requires complex chemistry, which requires heavy elements, which require several generations of stars to produce and distribute. It takes billions of years for a universe to become capable of producing beings who can wonder about it. And that process happens to occur in the same general era when the universe is still observable. We are not just observers, we are timely observers, cosmically lucky. The universe had to wait 13.8 billion years for beings capable of asking, "What is dark energy?" And by the time such beings arose, the answer was still accessible. The data was still there. The galaxies were still visible. The microwave background was still detectable. In 1 trillion years, questions about dark energy will be unanswerable because the evidence will have vanished. But today, the questions can be asked and partially answered. You are part of that answering. Even if you're not a scientist, you're participating in the human project of understanding the cosmos. You're listening. You're wondering. You're letting these ideas drift through your mind as you fall asleep. That matters. Not in a grand, universe-altering way, but in a quiet, human way. You are the universe becoming aware of itself, and you're doing it at the best possible time to be aware. So as you drift into sleep, let this thought settle over you like a blanket. You are here at the right time. The universe is old enough to be interesting and young enough to be understood. The darkness hasn't won yet. The stars are still shining, the galaxies are still visible, and you are awake or almost asleep in the only moment that matters. This one. Now we come to the end, not of the universe, that's still a long way off, but of this journey. We've traveled from your room to the edge of the observable cosmos. We've traced the expansion of space from the Big Bang to the present. We've encountered dark energy in all its strange, invisible, inexorable power. And along the way, perhaps without noticing, you've learned something important. Not just facts about cosmology, although those are valuable too, but something deeper, something about the nature of wonder itself. Dark energy is, in many ways, the ultimate mystery. It constitutes the majority of the universe. It determines the fate of everything that exists. And yet, we don't know what it is. We have names for it: dark energy, cosmological constant, quintessence. We have equations that describe its effects. We have observations that confirm its existence. But when it comes to the fundamental question, what is this thing? We have only guesses. And somehow, that's beautiful. The universe is not fully explained. The story is not complete. The deepest questions remain open, inviting exploration, demanding humility, rewarding curiosity. In a world that often feels overmapped, overexplained, and oversimplified, dark energy is a reminder that mystery endures, that the cosmos is stranger than we imagined, and likely stranger than we can imagine, that there are truths waiting to be discovered by minds that haven't been born yet. This is what wonder feels like. Not just amazement at something beautiful, but confrontation with something incomprehensible. The recognition that reality exceeds understanding. That the universe is not a puzzle to be solved, but a mystery to be entered. Dark energy invites that entrance. When you think about dark energy pushing galaxies apart, accelerating the expansion of space, steering the cosmos toward an empty and silent future, you are thinking thoughts that no human could have thought a century ago. You are engaging with ideas that emerged from decades of painstaking observation, clever theory, and creative insight. And you're doing it from your bed, in the dark, as you drift towards sleep. There's something almost absurd about that, and something wonderful. You are a creature made of atoms, organized by evolution, sustained by the nuclear fusion of a nearby star. You exist on a small planet in an ordinary galaxy in a vast, expanding universe. You will live for a few decades, a cosmic instant, and then return to the matter from which you came. And yet, in that instant, you can hold the universe in your mind. You can wonder about dark energy. You can ponder the fate of galaxies. You can feel, however faintly, the awe that comes from contemplating the infinite. That capacity for wonder is, in its own way, as remarkable as dark energy itself. The universe didn't have to produce beings who could understand it, or try to understand it, or lie awake at night thinking about it. But it did. And you are one of those beings. Tonight, let that be enough. Let the mystery of dark energy settle into your mind, not as a problem to be solved, but as a gift to be received. A reminder that reality is vast and strange and beautiful. A prompt to keep wondering, keep questioning, keep looking up at the stars. And now, as the darkness outside your window mirrors the darkness between galaxies, let yourself drift. The universe is expanding. The galaxies are receding. The future is long and cold and strange. But you are here. You are warm. You are safe. And for now, for this moment, that is all that matters. Good night.